because when I was proposing this topic, I didn't expect this actually to be a solved problem by the time we are presenting. It is not entirely solved, but we addressed the majority of it. But nevertheless, I would like to tell you what the problem was and how it was addressed. And for this, uh, I would like to give you a short introduction into this problem space. Let's give you time management first, and then we'll go for the problem description from Thomas Ilsche. Thomas works at the Technical University of Dresden today, and he did a lot of work and contributed a lot of good work in this problem space. So you'll yeah, listen to Thomas, and then I will tell you what was changed in the kernel, and we will show you some results for that going forward. Okay, so CPU idle time management. So obviously, very often it happens that there's no work for a given CPU, like it doesn't have anything to run. So in that case, we want the CPU to go into a state in which it will draw less power than in a working state. And so the CPU hardware offers us or allows us to put CPUs into a number of different uh, idle states or C states that are low power essentially. If a CPU is in an idle state, it doesn't execute instructions. So it can be power gated, it can be clock gated, power gated. So depending on how deep you want to go. And obviously, if we go very deep, then it will take a lot of time to wake the CPU up from the state. So there are hierarchies of those states, and this graph or diagram shows an example of a hierarchy of idle states in an Intel CPU. And so the gray area is a package, which roughly corresponds to a cluster in the ARM configuration. But the boxes here are CPU cores, and each of them has two hybrid threads or hyper threads if you use the terminology. So each of the hybrid threads can request the number of idle states. They usually are the numbers of them are usually from 1 to something like 6 or 7, or even 10 on some processors. And in this particular, and there's a hierarchy of states. So if both of the hybrid threads in the same core request a deep enough state, then the core as a whole can be put into a corresponding core state. And if all of the cores are in a deep enough idle states, then the package as a whole can be put into a corresponding idle state for a package. And obviously, if if the package idle states are the ones that allow us to save the most energy, right? Because putting the core itself into an idle state may not give us as much energy savings as doing that for the whole package. So here we have the hardware threads CPU0, CPU1 requested C2 and C3 respectively, and then the core could go into the core C2. In this case, it is C3 because the shallowest state requested was 3. And in these two cores, both hybrid threads requested C6, so the cores could go into the core C6 state. But the whole package can only go as deep as PC2 because of this core that is in that C2 state. So depending on what happens in each core, in each hardware thread and in each core, this whole hierarchy can go into a certain idle state. Okay, so this is how it works. There are states, if the CPU is part of an SOC, there are idle states for the whole thing, and then if all the if all the CPUs requested a deep enough idle state, then the whole package can go very deep, and then the SOC could also be put into an idle state, you know, for the whole. So the way it is handled in the kernel, you this roughly. So the CPU scheduler knows when CPUs are idle, and if that happens, it calls the CPU idle subsystem to first estimate the idle time, then select the state for this logical CPU, so hardware thread, or depending on the level at which logical CPUs are, then the state is entered, and the CPU stays in until there is an interrupt, and it's woken up and goes back to the state. However, there is one little complication, which is that this part is non-deterministic. So the estimation of the idle state generally depends on the history. And that can go wrong sometimes. And that leads to problems. And so now I will, either for Thomas to tell us about those problems or to dispel them.
So thank you for the introduction. So yeah, my name is Thomas Ilsche. I work at TU Dresden at the Center for Information Services and High Performance Computing. So it's a bit important to know that my background is HPC, so large fat Intel nodes usually. And also I'm from academia, as you can see from all the funding agencies at the top. So I'm happy to speak today, discuss with you today, like a real impact problem for many people. Okay, so a bit of my background is that I do energy measurement and energy modeling for HPC in terms of energy efficiency research. So we have a lot of instrumented systems, very fine-grained power instrumentation. We have certain systems where we look at a very deep level in terms of time, in sorts of microsecond resolution for single nodes, and also trying to get a bit more the resolution, what's the socket consuming, what's the other components in the system consuming. And the other part is that we also do large-scale instrumentation. So we have a production HPC system, petascale cluster, is 1400 nodes that's fully instrumented, every node of it is 1000 samples per second power instrumentation. And so this allows us to observe some things in practice and also in academic, synthetic situations. And most of the systems are also tuned for low idle power consumption, which is an important aspect. So what we saw about a year ago was that we had a system, even though it was tuned for low idle power consumption and really nothing was running, there were some mysterious spikes of power consumption for several seconds. So the power would just go up, sometimes totally in idle, sometimes after you did something like reading an MSR, it would stay there for several seconds and then go down again. And so at the time, on like a Haswell system, it was mainly distributing, disturbing our measurements. It was a big problem for getting a good power measurement, but it wasn't so much of a impact on average power because it occurred quite rarely. But now, since we installed a Skylake dual socket system, we actually see this this chart here, which is total idle, and nothing's running. And this is a typical installation. So we just installed Ubuntu server on it, nothing else, no other configuration, no daemons, no servers, no network traffic, and it will look like that in terms of the power consumption over time. So before we dig,
No, sorry, I was just looking at this scale.
Yeah.
So these are big machines.
Okay. Okay. Yes. So these are both dual socket machines. This is a Haswell machine with 24 cores, and this is a Skylake machine with 36 cores. So, I just arrived. Yes. Just to give a little bit of more background on the power scale we are also talking about, I measured also all this physical wall socket measurements. So this is total system power, some server systems of the last generations, and some desktop systems. So this is from Skylake to Sandybridge, and this is the desktop equivalence. And also I have an Epic system now. So we have another vendor here, but unfortunately we don't have an ARM system. So what we see, especially on the latest server systems, is that the green bar is everything is in the highest package C state we were talking about with Rafael before. And the blue bar is just a single core going to a C1E state. So what you can see is the impact of a single core going into a different sleep state. There's no activity on the core, right? It's not executing any workload. It just goes into a different C state. Is very high. So we go from 70 watts to over 120 watts just by a single core. And then just adding the other cores doesn't even add much more, right? So this is particular with the latest generation of hardware, as we can see for the Skylake and the Epic system. It wasn't that much of a disparity before, but it seems to be growing apart. We don't see the same effect for the desktop systems, at least for the 4-core systems. I think it has a lot of to do with the number of cores. But I don't want to go too much into the detail here. So now to understand more of what was happening in these specific instances, we saw the power consumption go up for these cases. We have a measurement. It's a very passive measurement. Use a perf event for recording the SCAT switch events and for recording the power CPU idle state. So we know whenever something is scheduled, and we know whenever some C state is entered or requested to be entered by the operating system, and we have an external power measurement which is no impact on the system itself. It's recorded on a totally different system. And in this case, the power measurement is for a socket. So it's a DC power measurement for both of the sockets in the system. And what we see here is a time range of about 3 seconds. Every core except one core is in the deepest C state, which is C6, and one core is in C1. This is a core on package 2 or package 1, whatever you count. But we see both sockets are going high up in power consumption over this time. And what we know is there's nothing scheduled during that time, so it's not waking up or anything. So if we look closer to where this whole thing starts, we can see the following. So this is now showing the scheduled processes for each CPU. And there's one CPU, I don't know if you can see it in the back, it has 4 tasks scheduled after another, which is just a K worker, and there's also some activity on other cores with K workers and JPD for a disk in the system. And this is in just about 100 microseconds. This task is scheduled 4 times. And you see this here in the activity of the state. -1 means the task is scheduled. And then after the 4th time the task was scheduled, it goes into C1. And this is because the heuristic of the governor selecting the C state just thinks it was waking up so quickly last time, it will probably wake up quickly again, but it won't. So we know that 3 seconds later, only this core is woken up again. So it went in the wrong C state. So this didn't happen on the other cores. There may be some interactions with some tasks on the other cores. It's hard to tell. But this is also only one example. So it's kind of a complex interaction between the hardware and the kernel. So I've tried to separate it into a cause, a trigger, and the contributing factors. So what I say, the cause of the problem is that the heuristic in the governor is sometimes wrong. There's no way around it. It's just not deterministic as we are talking about. So we cannot expect a perfect prediction. So in practice, it uses some repeatable timer as a repeatable interval detector with like 8 data points, but you could improve it a little bit by making a better heuristic, but you won't get the heuristic perfect. So we know that the C state is selected, that's not optimal. So the trigger is just a workload that causes this issue. I said cause. Is basically short sleep phases on one core after another, like we saw in the previous picture. And we've seen various sorts of triggers in practical systems, like interaction between K-workers, like journaling daemons, screen sessions, shells, lots of workloads where there's a ping pong between processes who do IPC and they are scheduled on different cores. And I also show another example of the Lustre file system in the next slides. We can also create a synthetic program that causes this issue reliably by just having a program setting a timer for a few microseconds, waking up 8 times, and then sleeping for a long time. So you can have a workload which is synthetic, which has 99.9999% idle, but which will have a huge impact on the power consumption. And there are certain contributing factors that really make this a practical issue. So first of all, I said our systems are optimized for low idle power consumption. And this is a bit paradox in the sense that if you idle for a long time, you will not have the chance to correct your mistake in the C state. So if you really get the background noise done, you reduce all the daemons, and it can take 10 seconds or longer to even wake up from the wrong C state. There's no mechanism that prevents you from being in the wrong C state for a long time. There's also the heuristic being a bit stubborn, because if you have a long sleep state after a few short sleep states, since it's just an outlier, and it will discard the long sleep state. And so it may take several wake-ups to even correct the wrongly selected C state. And last but not least, the impact of a single core being in the wrong C state is really making the difference whether this will affect your average power consumption or not. And this is why we see such a large increase in power consumption on the big server systems. Okay, so here's just another example that we found on an HPC production system. So this was really sort of an effect. We studied it for a while, and we understand how it works, and then we saw it everywhere. Everywhere we looked in just enough detail, we saw this effect. And so this is the Lustre file system, which is used on many HPC systems. It has a background task all running in the kernel drivers for ping to the server, I suppose. And there's a lot of interaction, and this is like the scheduling pattern on the system in like 2.5 milliseconds, what's happening. And after this kind of scheduling pattern, we can expect the predictions to go wrong. So this is what it looks like. And again, this is an example from a production system with 1400 nodes. And every 25 seconds, we have this ping, and it triggers a power nightmare. Oh, I didn't introduce the term yet. So we use the term power nightmare because it's a bit of a complex issue, and it's sort of catchy. I don't know. Some people may not like it. I don't know. This Lustre activity causes this issue, and it can take about a second. So this HPC production system is not that optimized for idle power consumption, and because fortunately it's an HPC system, it's supposed to be running all the time anyway. So yeah, what more is there to say? But anyway, it also increases power consumption very significantly for this phase, as we can see in the energy instrumentation. And we will fix the issue. I mean, the issue is not as long and persistent because there's a little bit more background activity on the production system, like logging activity, scheduling activity. Okay. Yeah, so I mean, right, you're sleeping, but it's a really bad sleep. So that's why it seems a bit fitting. And like always saying idle governor menu heuristic anomaly power, this is a bit iffy. Okay, so I want to just mention also my co-workers. particularly Markus Hähnel, who is working in the OS group, and also Robert Schöne, Mario Bielert, and Daniel Hackenberg, who are working with me in the Energy Efficiency Lab at the HPC Center. And so we published this issue on an HPC conference and also got into discussion with the Linux community. And we also have some tooling infrastructure that allows us to use perf event open and some visualization tools to really look into the millisecond range for these issues, and also always correlate the physical power measurement with these measurements from the kernel.
So that question about that. In particular, can I give you patches to test to run on your system?
You know the answer, right?
Yeah, well.
I think I tested about 10. I'm going to test 10
but
more.
my question is rather like, if I have a patch that somebody claims will improve, power on servers in a great way, right? Can I just give it to you and can you run it and see if you see any from it?
So I cannot run it on the 1400 node production system, but I can run it in the lab, especially if you need if you need a detailed look on the energy instrumentation. That is very beneficial. I mean, like recording perf events, you can do it on pretty much any server system. But having a power measurement with 2 million samples per second besides that and correlating with that, I guess that is something where we can really help.
Yeah, okay, cool. That's great.
Okay.
Do you have like 7, right? You have you say that you have a stubborn thing. Obviously. Just wondering if you had emotional picture on it.
So we discuss in the paper in detail whether you can use the auto demotion. So auto demotion is, I believe, from C from C3, and there's auto undemotion, but there's no auto promotion. So, but we did not have auto demotion enabled. We also looked at the residency counters from the hardware, and in our cases, the residency counters from the hardware were consistent with what the software requests. This is not obviously true for very short workloads. But if you were talking about fixing the issue in the hardware, you would need to have auto promotion to C6, and no such thing exists to my knowledge.
Thank God.
Yeah, that would be bad. I mean, that's we can't guarantee anyway.
Just saying, right? Okay, going back to was there another question?
Well, I was curious. I mean, do you have any proposed solution for the?
This is perfect because I was going to talk about that. So in our original publication, what we did, we made a fallback timer. So we recognize that it's not possible to make the heuristic perfect. There are many ways you can improve it, but you won't get it perfect. So what the most important thing is to prevent you from sleeping for such a long time in the wrong state. So if there's a chance for this to become a power nightmare, you want to have a timer to wake up from the wrong C state and go into the right C state. And this is what we did in just a proposed patch a while back. It was a bit hacky because I'm not the full-time kernel developer. It worked for our cases, but I think we now have a better solution with Rafael because we can use a different timer. I don't want to spoil it too much. We discussed also the auto promotion feature, which really doesn't exist, I guess. And fixing the heuristic, but it's not perfect. Yeah, and the other reference is just for our power measurements, which helped a lot in this case to really dig into the issue.
So now it's like
yes, it's
okay.
Your turn.
Yeah,
you have the honors of showing the improvements and solutions.
Yeah, okay.
Don't forget the last 2 slides.
Yeah, okay. Cool. So we can start over from this point. Let's go here. So I ended up with this slide. If you look at the idle loop in more detail, then it turns out that the first step in it, in 4.16 kernel, as of today, is to try to stop the scheduler tick. And it, most of the time, it actually stops. And then, after stopping the tick, we will look if there is something to, it's scheduled. If not, then we'll call the idle subsystem to estimate idle time and then select the state. Okay, so here's where the problem happens. Because the schedule, the idle governor uses the heuristics that to select to find out how long the CPU is going to be idle, and if that goes wrong, with the prediction, if it mispredicts, if it's not accurate, the resulting idle state may be too shallow, and then the processor will stay in this idle state for a long time, possibly causing the problems happen. This has another side. So this is one side of the problem. The other side of the problem is that this is overhead, because it takes time to stop the scheduler. You have to reprogram the hardware, and if we don't have to do it, why do it? Right? Because we can save time this way. And people saw this problem already before, and they worried that we stop the tick unnecessarily, because then we start doing idle for a very short time, and then and I tried to fix it in many different crazy ways, but I'm not going to talk about this. Okay, so how to fix this? And the answer is you have to redesign the idle loop. And then you can fix both sides of the problem. First, you can avoid stopping the tick because and second, you can use the tick as a safety net to wake the CPU up if it is in a wrong idle state. So now what happens today, and I mean 4.17 RC1 has this already. So this shift, and I will comment about it.
Yes, so that second point won't work if the tick is too short, right? Depends on the length of the tick, the granular. So the wake up, if you put it in the wrong state.
You mean this?
You said that the tick can help.
The tick can help, yeah. I will tell you why in a while. So the idle loop is no different. It first calls the CPU idle subsystem to estimate the idle time and then to select the state. And then it will consider stopping the tick, depending on whether on what the predicted idle duration is. If it is shorter than a tick period, it does not matter. The tick will be running. And this is this case. And then, no, it is not stopped. Yeah. But if the predicted idle duration is long, you can stop the tick and do all those things. So it will just go this. Yes. Okay. And that helps because now, if the idle duration is below the tick period, we will not stop the tick, and the tick will wake up the CPU. So if we are in a shallow idle state, the tick will wake up periodically. Done. And now we avoid the stopping the tick if we don't have to stop it too. So it is a double benefit from this change. So I want to comment on this. So this shift in 4.17 RC1 yesterday, and that was a I think a very good example of collaboration between various people. So for the bundle porters, Thomas and another guy from Canada, I believe, and code reviewers Peter and Frederick, and many thanks to Frederick for going to code, and I was developing the package. So together we were able to come up with the solution and to put it into an RC kernel in a very timely way, which I'm happy with. Needless to say. Okay, so now let me show you some results from some impact of this change. This is idle time. No idle time, idle power, sorry. Idle power from the Intel OTC server power lab. So this is the graph is like average idle power over the previous period. So the time is divided into short intervals. We measure power over the previous interval and plot. This is what the graphs show. And these are 4 different server systems. For quad-core Skylake, this is a Knight's Mill, which is Knight's Mill, which is a new generation of Knight's Landing. And these are dual socket Skylake servers. So the scale is different on this graph in particular. So have a look at that. So and the green line is before the change, and the red line is after.
What's your workload again? Sorry.
Idle.
Just idle.
Just idle.
Wow, these are systems that idle too.
Yeah, so they are idling at below 200 watts. That's the big. But this is okay. But yeah. So but in this case, it may go up as much as to 300 almost. So it is 100 watts of a difference. Yeah, temporary, but still. If you draw an average, it will be like 250 probably in this case. So we say 50 watts on the average per system in idle after this change. Okay, so this also looks nice, and you can see that this is a system. This is an unusual system. This is a very massive multi-core chip. So if there is an effect like that when one core goes like to the wrong state, then it will light up the entire box, and then this is what you see. It will jump like this. Okay, so dual socket are a bit better without the change, but still after the change, we'll see that the idle power is almost flat on all the systems. Well, otherwise it was like first noisy and second much higher. Okay, so another bunch of systems. And in particular, this one is interesting. This is a quad-core Broadwell system. Power floor is 300 watts for this. And in 416, it was high about this. It was between 300 and 400. So this is Knight's Landing, the original Knight's Landing. Also showing a lot of like wasted idle power without this.
But it has worked hard to do.
Yeah, Haskell is fine. Basically, yeah. But and I think it's quad-core. So
That's the one I had.
something happens in the newer systems that
The idle flow.
yeah, and I will comment on that. Just this is and it's the Broadwell system I was talking about before, and each of the dots in this graph is the individual measurement. So you can see that not only the average is a bit jumpy, but there's a lot of noise. Turns out this noise is introduced by instrumentation part, because we have run an IPMI, a process to read the IPMI data on this system, on the system itself, because it doesn't work on.
That's what we have the MCU for, but
Yeah, but it doesn't work. Actually, yeah. So we have to run a process to read the data from IPMI on a system itself, and that causes the noise. Plus turbostat causes the noise. Plus there are a few other sources of the noise, but the noise is just huge. There is some noise here too, because the noise doesn't go away, but this is limited. Like a bit of noise you can see, and here the jumps are like over up to like 450 watts in some cases. So the system basically goes to the turbo range in idle. Yeah.
I mean, it looks like there's a certain level on top, right?
Yeah,
Yes,
it is.
Probably just each and
Yeah.
every socket leaving the system.
Probably, I think so. So yeah, there is a lot of noise, which we can reduce just by redesigning the idle loop the way we're talking about.
Yeah, it looks by model. So
It looks by model, yeah. But there are outliers like above this. Like, I think it's like this is 100, so this will be 470 maybe.
So we've seen previously like 3 levels on a dual socket system. Like occasionally it happens on both sockets as another step. It's not as far off as the first step,
Yeah.
but then there's like the second
Yeah,
step
so
on top of
probably
that.
there are more package systems.
And of course you have to do some averaging, so that's
Oh,
why
sure.
there's stuff in between.
Question?
Yeah, I mean, out of curiosity, without looking at the facts, was it only a localized change in the idle loop, or did you have?
No, it wasn't. You had to redesign the numbers code with the
Oh, okay.
yeah, to work. So
For
in order,
ordering the
I will say let me go back to the flow diagram. So the reordering of the stuffing of the tick with this was
Yeah.
not trivial because we had to reorder because this needs to know how much time the CPU is going to be idle. So how much time this needs to know the next timer event time. And so you need to compute when the next timer event will happen.
but
in case-
discard the tick.
Yeah,
But
but
discard the
case
tick,
you
yeah.
but discard the tick. Yeah.
So we touched the no hertz code, we touched the timer code, we touched the idle loop, and we dropped the governor.
Yeah, we
Because there's-
covered also.
There's other problems. Well, will you touch on that? Why we needed to? So if you do leave the tick running and the tick wakes you up, and it is only the tick that wakes you up, you don't want to count that as an actual wake up for the governor because then you have the downwards bias. So you need to detect this situation and then actively fake the governor as no, we were sleeping longer. It's just you woke us up for dumb reasons.
So we needed to tweak the governor too. So the numbers go, the governor, the timers, and because of this dependency on the information of when the next timer event is going to happen. With the stop tick, which was the previous situation, that's easy because we know it. We stop the tick, so we know when the next timer event is. But here we have that there may be 2 different situations. One is with the stop tick, and the other is with the tick running, and we have to take both into account in this computation here. So it was not trivial, but not rocket science, as Peter said at one point. Okay, let me show some more graphs. How much time do you have?
5 minutes.
That's fine. So these are results from Dax Mighty School as one of the bug reporters for this problem. And this is not idle. This is, what is this? Oh yeah, it's 100 load on one CPU in a multi-core system. I think it was Ivy Bridge. So the blue line, you can't distinguish between blue and purple probably, but the blue line is something like this is the blue line, and this is the reference in course 16. And the red line is our kernel after the changes.
So can you repeat again what's blue and purple?
The blue is 416, the purple is something intermediate. So this is not the graph for me, so I just had to use what was important.
I think the purple is the changes to the governor and all stuff. And then there's another green line.
Oh yeah,
Because
because the patch set actually has 2 parts, and you can test the 2 parts separately, but actually they are complementary, so it does much sense. But that's what Doug did.
So I think one of the most important changes for the point part is that it allows you to escape a C0, not C0, but yes,
Zero, yeah,
the
zero.
C0
So
false
for the DAG's problem, actually, the problem was that this view. So on x86, we had a fake idle state, which is a polling state, and that's for latency reasons. And the problem was that on the DAG system, the CPU could go into this fake state and stay there like for a long time, spinning, and just spinning and just wasting energy. And that's the effect of that we can see here, for example. So the DAG used a workload with one CPU running 100% loaded and the other CPU idle. Okay, to trigger this. And then what he saw was like a power consumption going up to 32 watts on the system, where it should stay at something like 26. Okay, so this is this workload. Another example, a 145 test. So the reason why the red line is above the green is because the performance is a bit better with the red line, and then green is slower a bit. But the difference in power is really small. And then again, reference is one of the darker lines. So it doesn't matter of what you see because this is noisy. Each of them is nice. So it's this one actually, the one with this big here in a power draw. So again, a large impact on a workload like 145 test on this particular system. This is interesting. So that was basically using the Intel T-state driver. Test is different use cases or different tests, granted different tests. But this is with specifically with the scheduling governor. And there is a problem with the scheduling governor or on Intel with, I think, the soft lookup webdoc, which is the real-time task, and which because the scheduling governor don't have the frequency. So with 416, and this is this line, okay, with 416, if you run, so he used the workload where there was a work injected every some time, and the frequency was selected specifically to trigger this problem. So this line is particularly bad on purpose. Okay. So he used this frequency to trigger this particular problem, and he saw that okay, if you do some a tiny piece of work every once in a while with this frequency, then your power is actually never going down and is staying at a high level, like twice 50% above the level it should. With the changes, you get this flat red line here. So 50% of the difference in power growth in this workload. So the conclusion from that is if you had some strange behavior with the scheduling governor related to real-time tasks, then it is good to retest after this. Yes. Okay, I will now give the floor again to Thomas, and we'll see some more graphs.
Okay. Just to round up the results, so we can take a look into the details of what's happening with the wake-ups and fixing the C-state. Now we have to recognize the time scale is now about 100 milliseconds. This is a synthetic workload which reliably triggered these power nightmares before the change, and it's just waking up the processor 8 times in a row very quickly. And we see that after this synthetic workload, for a few ticks, it goes into C1E instead of the deeper C6 state. But after a short amount of time, in this case, it was, I think, like 60 milliseconds, every core gets into the right C state. So like on average, you won't see this, right? This is a synthetic workload, the worst case behavior, basically. And now the worst case is that it takes you, 60 milliseconds to fix the problem, whereas before you could stay in the wrong C state for 10 seconds. And maybe in some patch we can even get it a little bit to the left, so we only have to have one wake up. This is because of the outlier detection in the governor. But I think this is still a great improvement. And you see the effect on the power consumption here also.
Why is it 60 milliseconds? Because just a tape, right? That
Well, it's the governor.
You have to convince the governor that you sleep for longer. So in this case, I'm pretty sure this was 250 hertz kernel. So you have 4 milliseconds. It's actually not 60. It's more like for these. This is a bit of an outlier. It's a bit weird. Let's say it's 50 milliseconds. Okay. You were also asking previously about I will rephrase the question: is the tick always a good fallback timer? And the answer is not, but in practice it's fine. So you can imagine scenarios where you have idle states that have residency times, which means the minimum amount of time you need to sleep to enter them, that are longer than the tick. This is the case for mobile platforms, this is like C6, C10 C states, but not for the affected server platforms. So right now, I think it's 800 microseconds, and if you run whatever hertz setting you have for the kernel, you have either 1 millisecond or 4 milliseconds, something like that, for the timer. So that is fine in practice. You can construct academic situations with artificial workloads where it's still a bit of an issue, but like in practice, we don't see this anymore.
Yeah, but then adding timers, because we will require to adding timers will require us to we'll introduce more overhead, because then we will need to reprogram the timer.
Yeah.
So and this way we avoid doing this essentially.
So that was the complaint from the network folks, is actually stopping the tick and restarting the tick
yeah.
is very expensive.
Yeah,
You have
so-
to reprogram timer hardware.
Yeah, so this is the other side of the problem I was talking about, right? This is the overhead of stopping the tick also is regarded as a problem, and which is related to programming the timer hardware. So if we added more timers, we would just introduce more overhead. That was not.
Yeah, so that's one thing. Like in our proof of concept fix, where we had the fallback timer, just an extra timer. On our systems, it was running fine. But I guess what we don't have the chance is to really see the broad use case for Linux on so many different varieties of hardware, and like adding some new timer may have no overhead effect on this system, but on a different system it has an effect. So that's why it's a kind of an elegant solution to reuse the scan timer, and it works very well in practice. So this is the final slide here. So that's what it looked like before this default Linux installation. It's Linux 4.4, but I could have just placed Linux 4.16. There was no change in the behavior. And now it's this really nice flat measurement. It's a little bit more detailed, a little bit more time resolution than the previous chart, but the idea is really the same. You have two states, you jump between the states, and now everything is good. So we get the power down by 10% on this system, maybe a bit more on another server system, but I think the numbers are fairly universal around that range. And like I've seen people pick up this 10% number and not believe it. Yeah, but let's try it.
Okay. One side question. Have you guys considered looking at how this behaves on smaller systems on us?
So I, for once, don't have a mobile device with such a detailed power instrumentation. We've looked at the desktop systems we showed previously. We can produce the issue there, but just because of the difference in terms of how the package C states react, the effect is much less than
But the
on
problem is
server
still there.
systems.
Problem's still there, right?
The
problem
yeah,
is still
the
there.
The problem
there,
is still there, right?
Just on the same scale.
It Yeah, you can see the anomaly if you look for it, but the power consumption is not as much affected.
No,
At least right now, but I mean, I don't know, what if we have a mobile system with
Yeah,
64 cores?
Really, we
in
have
2
similar
years?
problem with mobile. We have such kind of problem where the CPU of the cluster stay in a shallow state for
Yeah.
a long time.
So you
this
will,
will help.
yeah, you will see this as long as you have more than one idle state, and then per CPU, and then there is enough difference between the idle states. So
Yeah.
Really, this will help.
Do you know by top of the heart what the residency times for the highest C state is on ARM?
Oh, that depends.
But there isn't one.
That it's extremely
There is
slow.
one. A million houses.
Yeah, so
Yeah.
so a few. So I grabbed the kernel code and from the platforms that have DTs that have this information in the kernel tree, there was one or two that had like 20 millis.
They are wrong. They are wrong. We have to update
It's a
that.
way to prevent them to enter a deep state for
We need to update that.
responsiveness.
Just wrong. They just put some numbers.
I mean, we can have a long discussion that all the residency times
Yeah.
are wrong. I think the residency times on Intel are wrong, because we can, I mean,
They're
sorry.
Okay, I mean, honestly, this is, if I were a hardware person and you asked me a question, I would just shrug. Like,
Yeah.
you know, yeah, maybe 100
So-
or something like that, because so the residence time is really the target residency, which is how much time you should
It's the break-even time.
Break even, yeah.
So we have
break
some
even.
script to try to find this one.
And then, so it is roughly the time you need to be in the state for it to make sense.
Yeah.
But roughly. And there are idle states on USOCs with target residencies like 5,000 milliseconds. The FC10 on the new Katy Lake, for example. So.
Take that off the crystal.
Yeah.
So I have a bonus slide just really quickly. What we observed is actually like the residency time being 800 microseconds. You sleep for 800 microseconds, it's fine. And you have a certain point, you sleep for about a millisecond to 2 milliseconds. Actually, the power consumption goes up. And then you sleep even longer, then it goes down again. And you can even show like you sleep for 1.5 milliseconds. The residency time is 800 microseconds. And you really sleep for that time, but the residency colors of the hardware do not show that you sleep at all in this state that you requested. So we have to always also recognize that the state we say the hardware should go into is a hint to the hardware, and it doesn't necessarily do
Yeah,
that.
there
So-
is auto demotion, and on servers, actually, the way it works is actually the hardware runs an idle governor in hardware. In hardware on top of our idle governor. So it also tries to track the interrupts and so on, like statistics and predict idle duration.
Yeah, that's why I asked about the.
Yeah, I mean,
Yeah.
and there's auto demotion MSRs that supposedly tell the hardware to disable that, but apparently in practice they may not be as reliable as one would think.
The auto promotion is really, really bad for real-time systems where you, or anything where you want to put a cap on exit latency.
Yeah, the whole concept of was expire, like, there's two latency, but there's the break even and the worst case wake-up latency.
Right.
Get the fuck about worst case wake-up latency. There's a reason why. it's-
Yeah.
Yeah, that's yeah. Right. Okay,
And
so
auto promotion will completely screw that up.
Yeah,
we are, you know,
that's fine.
we have used our time window, so that's it.
Thank you.